Okay, so in this video, we're going to look at a few more examples and talk a little bit more about parametric surfaces. Okay, so let's say that we have, let's say that we have the following surface. So it's just, a general surface. This is just a general vector parameterization of a surface. Okay, now we can define two different families of curves. So if we hold either s or t constant, if you hold either s or t constant, then this just becomes, if s is equal to, say, 5, then r is just a function of the t variable, and so it's going to be a curve. So if you hold either s or t constant, we get a curve. Okay, and then if we say let's hold s constant equal to 0 and see what we get. Then let's hold s equal to 1 and see what curve we get. And let's hold s equal to 2 and see what we get. And then maybe let's hold s equal to 1/2 and see what we get, and so on and so forth. This is a family of curves. We get a different curve for every value of s that we hold constant. And we can do something similarly if we hold t constant. Okay, so if you hold either s or t constant, we get a curve. These families of curves are called grid lines. Okay, so let's look at an example. Let's look back at this cylinder, R of ST. So this is going to be the cylinder. This is going to be the cylinder, and now I'm going to make it centered on the z-axis. So it'll be cosine S, sine S, t. And for this, I'm going to say S is going to go between 0 and 2 pi. And we just want the top part of the cylinder. So we'll say 0 is less than or equal to t is less than or equal to positive infinity, or just less than positive infinity. Okay, so roughly sketching it, this is what we get. Okay, so use your imagination. This is not the worst work I've ever done. This is a sphere of radius 1 centered on the z-axis. Okay, so now let's look at what happens for various grid lines. So if you hold t fixed, so let's say hold t equal to t naught. Okay, so that means we're going to hold the height fixed. Well, what's going to happen? S is going to vary from 0 to 2 pi, and what we're going to get is just going to be a circle at the height z is equal to t naught. So it'll be something like this. Okay, and of course it'll be around the back of the cylinder, but I can't draw that. So this is z is equal to t naught. Okay, so the family of grid lines, when we hold t fixed, these are just going to be circles, going from the bottom all the way up to infinity or whatever. Okay, so the grid lines when we hold t fixed are just going to be these horizontal circles. So just given the way things are oriented, we might call these latitude lines. Okay, these are all circles, they're all parallel with each other. Okay, now let's see what happens if we hold s constant. Okay, this means that, the x and y, if you look at the x and y coordinates, it's going to be some fixed point in the xy plane. So some fixed point like this on the xy plane in the circle of radius 1 centered at 0. Because we always know that the x coordinate squared plus the y coordinate squared is equal to 1. So if we fixed s, if we hold s constant, sorry, this says constant, not, if you hold s constant, that's like fixing some point on this circle down here. And now if we let t range from 0 to positive infinity, so the x and y values are staying the same, but t is just getting bigger and bigger and bigger. And so this is just going to be a line going straight up like this, okay, on the side of the cylinder. Okay, and if we look at a few more of them, we'll get stuff like this. Each one of these lines that I'm drawing is for a different fixed value of s. And so maybe for these, we kind of want to think of them as longitude lines for the cylinder. Okay, and so this is what I mean by the parameters can give us coordinates can give us a way to give coordinates on this cylinder, because each one of these green lines corresponds to a fixed constant of s. So if you wanted to say use coordinates to denote this point right here, let's say you wanted to use coordinates to denote this point right here, you would just report that in whatever s value, whatever t value gave you this green line, and whatever s value gave you this blue line right here. Okay. Okay, so this is grid lines. Let's look at another example. Okay, let's find the parameterization of the sphere of radius 1 centered at the origin. Now, there's already kind of something not clear here. I'm saying find the parameterization. I should say find a parameterization, because there's many different parameterizations. So find a parameterization of the sphere of radius 1 centered at the origin. Okay, now for a lot of this stuff, practically to find the parameterization for a surface, you're just going to have to think about information that you know about this surface from other contexts, or not from other contexts, but from outside of the context of parameterizing a surface. There is, in some sense, there is an algorithm to see, say, given a surface, come up with a parameterization for it. And we'll talk about that a little bit later, but really it's just kind of useful to think about the information that you know. So, well, let's think about R3. So we have a sphere, we're in R3. The first thing that we might want to think about is to try to use spherical coordinates. Okay, in spherical coordinates, an arbitrary point of radius 1, an arbitrary point that is 1 unit from the origin. So a sphere is all of the points of 1 unit from the origin. So an arbitrary point that is 1 unit from the origin, let's say is given by phi theta rho. Well, notice that if it's 1 unit from the origin, we already know what rho is. Rho is equal to 1. Okay, because rho is a distance from the origin. So an arbitrary point, let me write an arbitrary point is going to have this form right here. R of phi theta 1, where this is just the spherical coordinates of a point. So this is just going to be sine phi cosine theta sine phi sine theta cosine phi. So what are the spherical coordinates? So if I say, what are the spherical coordinates of a point that is located 1 unit from the origin? This is what it's going to be. Because remember, what is x in spherical coordinates? X is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. Z is equal to rho cosine phi. Okay, so if rho is equal to 1, we just don't, there's a 1 there. Okay, right. So what this tells us is that as phi and theta go over a certain parameter domain, this is going to trace out a sphere of radius 1 centered at the origin. So now we just need to figure out what the parameter domains are. Well, remember, we know that by definition, when we're doing spherical coordinates, by definition, phi lied in the interval 0 to pi, and theta lied in the interval 0 to 2 pi. So this notation right here just is another way of writing 0 less than or equal to phi less than or equal to pi, and 0 less than or equal to theta less than or equal to 2 pi. Okay, so in other words, we can parameterize the sphere just by using the phi and theta parameters from spherical coordinates. And if instead of using phi and theta, you want to use s and t or u and v, that's fine. But typically, when parameterizing the sphere, we use the coordinates phi and theta. Okay, so once again, if you're having trouble understanding this, just go back and read a little bit more about spherical coordinates, because all this does is just come straight from spherical coordinates. What is written in spherical coordinates? What does an arbitrary point of radius 1 have? What form does that have? And this is the form right here. And now if you just let phi and theta go through this parameter domain, this will trace out the whole sphere. For every phi and theta, this is another point on the sphere. And as phi ranges from 0 to pi and theta from 0 to 2 pi, this is going to trace out the whole sphere of radius 1 centered at the origin. Now, another question that we can ask is, what are the grid lines? Okay, so let's get a sketch of this sphere. So again, just use your imagination. This is a sphere of radius 1 centered at the origin. Okay, so now let's think about the grid lines. So if we hold phi constant, if we hold phi constant, this means the z variable is going to stay the same. And then what we're going to get is going to be uh, circles of, so we're going to be in the z is equal to cosine phi plane. But if you look at the x and y coordinates, well, x squared plus y squared is going to be equal to sine phi squared. Okay, so then what we're going to get is going to be a circle of radius sine phi. If it's going to be a circle of radius sine phi in the plane z is equal to cosine phi. In other words, it's going to be stuff like this. So in the case of a sphere, when you hold, that's like the equator. In the case of a sphere, when you hold phi constant in this parameterization, you really do get latitude lines. Okay, I know my drawing is not that good. Okay, if you hold theta constant, well, this means that the cosine theta of x part of x and the sine theta part of y are going to be constant, but what you're going to get are going to be lines. As phi goes from 0 to pi, you're going to get grid lines that go like this. Okay, because when phi is equal to 0 or pi, sine phi is equal to 0. So this means the x and y coordinates are going to be equal to 0. And the z coordinate is going to go from, when phi is equal to 0, it's going to be 1. When phi is equal to pi, it's going to be minus 1. And so when you hold phi constant, the grid lines that you get are these like half longitude lines. I know these are bad. And now to get the other half of the longitude line, you need to add pi to your theta value, and that'll get the other half of the longitude line. Okay, so what does this mean? If you hold phi constant, you're going to get latitude lines. If you hold theta constant, these are going to be the longitude lines. Okay, and so these really are like familiar grid lines that we use on a map in navigation. So in later videos, and obviously in lecture, we're going to go over finding parametric equations or finding parameterizations for more surfaces. But in my opinion, it's something that really just takes practice. We're going to look at a few tricks. I shouldn't really say tricks. We're going to look at a few things that will help with that. But in reality, it just helps to get practice doing this. So as an exercise, come up with the parameterization of a sphere of radius 5 and just the part of the sphere that's in the first quadrant. See if you can do that. I mean, this is very similar to what you're doing. This is very similar to when we're finding regions to integrate over.